All right, chapter 16 is a continuation of aqueous equilibria. And recall in the last PowerPoint, we discussed the effect of the cation and the anion, how that makes the salt an acidic salt, a basic salt, or a neutral salt. And in that, we took a qualitative look that if you have a group 1 cation and an anion, like let's say chloride, so if you're talking about something like NaCl, NaCl, so that's a group 1 cation I was talking about, and this is Cl negative. If you put this in water, it's going to dissociate as Na plus and Cl minus. And one can envision perhaps that NaCl would have been formed by the reaction of HCl and sodium hydroxide. So if you wanted to figure out what the base component and what the acid component are, what you should do is that you should add the HOH of water. Of course, OH is negative and H is positive. This is a quick way to do that. So bring the positive to the negative and bring the negative to the positive, and so you would have sodium hydroxide and HCl. And since both of these are strong in nature, it's a strong acid, strong base combination, they undergo 100% ionization. They're going to completely neutralize each other, and hence the pH of such a solution is going to be exactly 7. On the other hand, if you have something like sodium acetate, which is made up of again, I'm going to add the HOH, and hopefully you can see that it's made up of sodium hydroxide and acetic acid. And of course, sodium hydroxide is going to completely ionize because this is a strong base. Acetic acid is a weak acid. And so in that case, the pH, the overall pH, is going to be greater than 7 because your base is strong. Likewise, if your acid is strong, your pH is usually less than 7. And if it is a weak acid, weak base, then you really have to depend on the values of Ka and Kb. I'm going to spend a couple minutes in discussing, taking a look at this mathematically. So we have a mathematical proof in addition to the qualitative analysis that we did in the previous PowerPoint. And from that point onwards, I'm going to go over buffer capacity, and then finally, we will end the chapter with titrations and the math. How do we go about the math? And we are going to take again a qualitative and quantitative look for both strong acid, strong base titration, as well as weak acid, strong base titration. So how we plot, what that means, I'm going to take a stepwise look from the exam's perspective, what you need to know, all of that good stuff. All right, let's go forward. Now, like we discussed earlier, we know that when a neutralization reaction takes place, a neutralization reaction meaning something like HCl in the aqueous phase is reacting with sodium hydroxide, which also is in the aqueous phase, and it gives you sodium chloride, and water is your product, H2O is your product. So your products are water and a salt of some kind. So the salt could be made by the reaction of a strong acid, strong base, could be a combination of weak acid, strong base, could be strong acid, weak base, or both could be weak. This is what we have seen previously. Before we actually go into the math of that, I really want to again take a step back and remind you of something, and that is anytime you're referring to any anion, let's say it's an A minus anion, that basically is a conjugate base of HA. So if I'm saying that this guy is a conjugate base, that means I have removed the proton. That is how you achieve the conjugate base structure. And again, those of you who have to take organic chemistry, don't forget this. This is a very, very important concept that's going to be with you, remain with you, even if you have to go all the way to pharmacy. You're going to be seeing this even up to that. So realize that conjugate base is nothing but a negatively charged anion, and since every anion can be envisioned as the conjugate base of an acid, every anion itself can be a potential base. So realize that not every anion will act as a base. It will have base-like properties, but how strong it is going to be really depends on how strong the corresponding conjugate acid is. And we discussed this previously, that an anion which is a conjugate base of a weak acid itself will be basic. It will be weakly basic in nature. On the other hand, an anion of conjugate base of a strong acid is going to be pH neutral. So that means it's going to be neither acidic nor basic in nature. So what that means that if you have something like HCl, and you remove the proton, and from there you're getting Cl negative. That means this Cl negative, which is an anion of a strong acid, it's going to be pH neutral. This is going to be pH neutral. No wonder sodium chloride is essentially pH 7. On the other hand, if you compare this to, let's say, HF, you remove the proton, you're going to end up with F negative. So F negative anion is a conjugate base of a weak acid, since we know HF is a weak acid. And so F negative itself is going to be considered weakly basic, and it is going to ionize water. So let's take a look. I said HF gives you H plus and F minus, and this F minus is going to ionize water. F minus is going to ionize water because it's weakly basic. That means you are going to be able to write down this F is going to attack, and you're going to end up with HF plus OH negative. Both of these are going to be aqueous. So anytime we say that a certain anion is a base itself, that basically means that it has the potential to generate hydroxide in solution. Now, we can understand why the conjugate base of a weak acid is basic by asking ourselves why the acid is weak to begin with. So going back to the fact, why is it that hydrofluoric acid is a weak acid? Well, you know that HF plus H2O in equilibrium, giving you hydronium and F negative. That means this particular equilibrium is more towards the left hand side, and it is towards the left hand side because the F negative has a really significant affinity for the protons, for the hydronium. And what that means is that when F minus is going to be put in water, it's going to interact with the proton pretty quickly, and it's going to remove that proton from the water molecules and ionize it, and thus it's going to behave as a weak base. So one can perhaps envision that weaker is the acid, stronger is the conjugate base. So if you have HF as an acid, it's going to have a stronger base. On the other hand, if you're talking about, let's say, H2O is your acid, the base, if you remove the proton, is going to be OH negative, right? So the base strength is going to be even more as compared to the F minus. So if you compare the two, water is a weak acid, but its base is strong base. HF is stronger than water, and that means that the base is going to be weaker than the hydroxide. Hopefully you can see that. All right, let's think about what happens in case of HCl. Now, HCl is a strong acid, so if you put that in water, it's going to give you hydronium and Cl negative. And actually, this equilibrium is partly wrong to actually write that. You should write down a single arrow pointing towards the products. This means that the reaction lies far to the right because the Cl negative does not have an affinity for the protons, and so consequently when chloride is put in water, it doesn't remove the protons from water molecules. So realize the difference, the subtle difference between HF and HCl, but it has big amplified effects. All right, having said that, I'm going to just take a couple minutes more to reiterate what we already have seen in the past, that we can actually determine the pH of a solution containing an anion of a weak base in a manner similar to what we have seen previously. So for any reaction like HA plus water giving you hydronium and A minus, and this A could be like acetate, it could be any weak acid, it could be fluoride. I'm just keeping it generic for now. You can write down the acid dissociation constant as hydronium times A minus divided by HA. We of course do not include the water because it's a liquid. And so you can also write down for the expression for the conjugate base, if you can see. So let's say this was, just for the sake of argument, I'm going to switch this to F because you just saw the example of that. So this is going to be F minus, this is going to be HF. And what I'm saying right now is that this F minus is going to abstract that proton off from water. So it's going to give me HF, let's write that again, HF plus OH negative is going to be generated. And this is all aqueous again. So what we are saying is that we have hydrolyzed the H2O. We have just broken that molecule off. And for that case, you can write down the Kb. And that is going to be HF times OH negative divided by F negative. And so if you add the two equations, so equation number 1 and equation number 2, if you add the two equations, you would be able to say that the HF on the left hand side and the HF on the right hand side, they're going to cancel each other off. Likewise, the F minus on the left side and the right side will cancel off, and you would basically have a 2H2O in equilibrium with H3O plus and OH negative, which in other words is a neutralization reaction. Also realize that if you have added two equations, that means you must multiply the K values. So Ka times Kb is going to be equal to hydronium times fluoride divided by HF times HF times OH negative divided by fluoride. Fluoride and fluoride cancel, HF and HF cancel. You're left with hydronium times OH, and that, by the way, has a specific name, Kw. And so one can say at any given point of time that Ka times Kb is equal to Kw. And for that matter, if you know the Ka value of a particular acid and you wanted to determine the Kb for that, you can simply do that by dividing the ion product, which is 1 times 10 to the negative 14, by the Ka number. So just to put things in perspective, let's say you wanted to determine that for for acetic acid. Now acetic acid Ka is 1.8 times 10 to the negative 5. So if I wanted to determine the Kb for what? Acetate. I would say that Kb for acetate, CH3COO negative, is going to be 1 times 10 to the negative 14. Divide that by 1.8 times 10 to the negative 5th, and that gives me an answer of 5.6 times 10 to the negative 10. And that's your Kb value for uh, the acetate. And now that you know the Kb value for the acetate, if you wanted to, you could determine the pH of the solution containing the anion of that base. Let's see if we can actually apply this concept to a problem. The question is, find the pH of a 0.100 molar sodium formate solution. Of course, you can see that if it's a sodium salt, it's going to completely dissociate into the formate and the sodium ions. And you also know that sodium ion in particular doesn't really have any acidic or basic properties, but formate on the other hand is the conjugate anion of a weak acid. And so you know that if the acid is weak, the base could be strong, so you can have an equilibrium for the reasons we have discussed, an equilibrium like formate plus water. So it's going to try to abstract that proton off to give you formic acid plus OH negative. And we have said that the initial concentration here is 0.1, and of course initially there is no formic acid, there is no hydroxide, but there can be a change so that hydrolysis can take place, which is going to give you X moles of the formic acid and X of the hydroxide. So when you sum it up to determine the equilibrium concentrations, they are going to look like 0.1 minus X, X for the formic acid, X for the hydroxide. Realize it's not necessary that you would be given a Kb value for a certain anion all the time. Sometimes it's a possibility that you could be given a table of all the Ka values, and the Ka value that's given for formic acid is 1.8 times 10 to the negative 4th. So what do? We simply use the relationship we just learned, that Ka times Kb is equal to Kw, and so Kb is going to be equal to 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 4th. So I have a value 5.6 times 10 to the negative 11, and I'm going to use that to determine the value of X. Once I know X, then I will just take a negative log of that. That'll give me POH. I have to determine pH, so we'll go 14 minus that number. So it seems pretty straightforward. Let's quickly take a look. Kb is going to be equal to formic acid concentration times hydroxide divided by formate. And I'm just going to plug in the numbers from my ICE table. X times X divided by 0.100 minus X. That kind of looks like X squared over 0.100 minus X. And that is going to be equal to 5.6 times 10 to the negative 11. This is what I'm going to try to solve. The question is whether I can use the approximation or not. My concentration is to the tune of 0.1. The K value is 10 to the negative 11. So the approximation is going to be valid since it's going to be way more than 100. And so I can assume, I can approximate that 0.100 minus X is about the same as 0.100. That means X is an itty bitty, really small quantity. So one can say X squared divided by 0.100 is equal to 5.6 times 10 to the negative 11. Or you can determine x as 5.6 times 10 to the negative 12, because it's 0.1. You can figure that out on your calculator also. And now I'm going to take a square root of that. So taking square root of both sides, x comes out to be 2.4 times 10 to the negative 6. But what was x? X was hydroxide. So if I have hydroxide, I pretty much have the POH. And if I have POH, I'm going to subtract that from 14, and that will give me pH. Alternatively, you can determine the hydronium ion concentration by dividing 1 times 10 to the negative 14 by the hydroxide, and then straight away take the negative log of that. So one way or the other, we will have the same value. Let's maybe do the second method. So what I'm saying is, let's change color so you can differentiate. Hydronium times hydroxide is 1 times 10 to the negative 14. And so hydronium, we're going to just plug in the value of hydroxide. 2.4 times 10 to the negative 6th, which gives me a value of 4.2 times 10 to the negative 9 molar. And once you have determined the hydronium, you know that pH is nothing but negative log of the hydronium. So negative log of 4.2 times 10 to the negative 9th. And when you plug in your calculator, I am getting a value 8.38. And that makes sense. Why? Because this number is more than 7, and my hydrolysis of the formate, my original equation, that had given me that formate is going to rip off that proton and generate hydroxide. So if you have hydroxide in your solution, you are supposed to have a pH greater than 7. So it tallies, it makes sense. Okay, so this slide again kind of reiterates what we have been discussing. If you take a solution of hydrochloric acid and you mix it with sodium hydroxide, since hydrochloric acid is a strong acid and sodium hydroxide is a strong base, they're going to go through complete dissociation to give H plus and Cl negative. Sodium hydroxide is going to give complete dissociation to give sodium ion and hydroxide ion, and they're going to switch the ionic partners, and you're going to end up with water and NaCl. And basically you're going to be able to ionize NaCl as Na plus and Cl minus, since it's a soluble salt of sodium. And you can hopefully see that as I have written the same thing over here, which is my complete ionic equation. Hopefully it's ringing some bells from Gen Chem 1. You have sodium on both the sides of the equation, so that's your spectator ion, which you can simply get rid of, just like Cl negative as well. And what you're left with is that a proton reacts with the hydroxide to give you water. And if you add H2O to both the sides of the equation, and the only reason you're doing that is because you always run aqueous equilibria taking water as the solvent. So this water is going to interact with the proton and give you the hydronium ion. So both of these are aqueous, and that will give you 2 molecules of water. Now, for this reaction, if you wanted to write down the overall equilibrium constant, you would say 1 for the numerator is divided by hydronium times hydroxide, and you will call this a neutralization constant. But guess what? Hydronium times hydroxide, we know what that is. That's Kw, and it has a value 1 times 10 to the power of negative 14. So hopefully you can see that Kn for this reaction, which is a strong acid, strong base neutralization reaction, the Kn comes out to be 1 times 10 to the power of positive 14. That's a pretty high number. And since this number is really large, that tells you something about this reaction. It tells you that it's going to go all the way to completion, and only the forward reaction would be possible in this particular case. And that's what I say here. This should be 10 to the power of the pH in such a case is going to be always considered to be equal to 7, and we say that the reaction is going to proceed with 100% completion because both the strong acid and the strong base completely ionize all the way to give you the ions, and so the forward reaction is going to be the more favored reaction in this case. Let's take a look how the result gets affected if you now switch from a strong acid such as HCl to a weaker acid such as maybe acetic acid or hydrofluoric acid. So something like CH3COOH or HF. Any one of those should be able to do the trick. Let's see how it's going to affect our overall neutralization constant. So I have here HF, and that's reacting with sodium hydroxide, gives you H2O and sodium fluoride. Now, realize if you were to determine, if you were to get the complete ionic equation, you're not going to ionize the HF in this case, even though you have the letters AQ. The reason for that is because it's a weak acid, it's not going to give you 100% ionization, so I'm going to keep that intact. Sodium hydroxide, on the other hand, is a strong base, so we are going to completely ionize that as Na plus and OH negative. Of course, you have your equilibrium. Water is liquid, so you're not going to ionize it, and sodium fluoride you are going to ionize because it's a soluble salt. So hopefully you can see sodium and sodium, they are the spectator ions. You get rid of that, and what remains is your net ionic equation. So HF plus OH negative gives you water and F minus. So if you now consider the equation, this is kind of the backward reaction, the way it's written. The backward reaction would be more favored. Hopefully you can see that. Because the F minus is going to rip off the proton and generate the OH negative and the HF, and so you can say that such a solution will be basic in nature because you have a strong base ultimately in your mixture. Now realize what all has happened in this reaction. When you would have taken a solution of HF, that HF would have interacted first with water, and it would have given you hydronium and fluoride. And there would be a Ka associated, which in this case is 3.5 times 10 to the negative 4. And I think this is a Mac and PC, which is why all of my equilibrium is shown as a box. And what else is happening is that we are carrying out a neutralization reaction. So we are quenching that hydronium ion by treating that with NaOH, and since NaOH gives you the hydroxide, this is the second reaction that's taking place. So 1 times 10 to the power of 14 is the equilibrium constant for that second reaction. So if you now add the two equations, hopefully you can see one water is going to get rid of one water here. Hydronium and hydronium will get cancelled, so you will have this equation. And the Kn for that is going to be, again, we are going to just simply take a product of the two. So when you put the numbers in perspective, Ka times 1 over Kw, just the way we did in class, it's going to be 3.5 times 10 to the negative fourth times 1 times 10 to the power of 14, and that value comes out to be 3.5 times 10 to the power of 10. And that's a pretty high number as well, lots of zeros. It's a high value, much more than 1,000, and we say that the reaction, this neutralization, will be a plausible, it will be a feasible reaction. It is a measurable reaction at that. You have the backward reaction for this HF component. So to summarize, what did we just see? We saw that the reaction is going to go, the neutralization reaction between a weak acid and a strong base is going to go to completion because because you have the hydroxide, which will have strong affinity for protons. pH is going to be greater than 7 though, because there will be a backward reaction. And just so let's consider, for a strong acid, weak base, what kind of a system are we looking at? Over here I have ammonia, which is my weak base. Strong acid is HCl, so you know that it's going to completely dissociate and give you H plus and Cl negative. So when the neutralization takes place, it really is just a proton transfer from the proton donor HCl to the proton acceptor ammonia, which will give you NH4 plus ammonium ion. And so the net ionic equation, hopefully you can see, can be written as hydronium plus ammonia, giving you ammonium and water. We are writing this as hydronium again because everything is run in water as the medium. So just the same way as we did previously, there are two things that are occurring in this reaction. Your ammonia is going to abstract the proton from the water. That's one reaction to generate the hydroxide and ammonium. The other reaction that's occurring is the neutralization of that hydroxide that gets generated. So two reactions that are occurring is hydrolysis of the weak base and then the neutralization. And hopefully you can see the same thing as we have seen previously. If you add the two equations, one of the water is going to get cancelled off, hydroxide and hydroxide will get cancelled off. You're going to be left with hydronium plus ammonia, giving you ammonium and water, which by the way is the reaction that we were interested in the first place. And so hopefully you can see that for this reaction, the K is going to be ammonium divided by hydronium times ammonia. And if you get your equations together, you would need to multiply. So in this case, we will write it as Kb times K. Let's write it as 1 over Kw because that's easy to see. And so you would be able to determine the value of Kn, the neutralization constant, which comes out to be 1.8 times 10 to the ninth. That is a pretty high value as well. And what does that tell you? That tells you that if you have a strong acid weak base type of a combination, that reaction will also go all the way to completion. You will see a complete reaction for this case, and the only reason why that occurs is because the acid is strong, so that drives the reaction in the forward direction. So what have we just learned? We have learned that the neutralization constant can be determined by simply multiplying the Kb for the reaction by 1 over Kw. And of course, it's 100% completion because hydronium ion is a powerful proton donor. The pH in this case is going to be less than 7 because the conjugate acid in this case is that gets generated is going to be strong. Okay, let's take a look at the final case, which is if you have a weak acid, which is acetic acid, and ammonia, which is a weak base. And your products, of course, acetic acid is going to give you the proton, is going to generate ammonium. But the question is, to what extent does this reaction occur? And really, the answer is that both the acid and the base remain largely undissociated. And the reason for that is because the Ka and the Kb for both the weak acid and the weak base. For ammonia, it's 1.8 times 10 to the negative fifth, and it is the same for the acetic acid as well. So both of these are pretty low numbers, and even though we are carrying out a neutralization reaction, an overall neutralization reaction, the effect is such that the neutralization constant for this can be determined by determining the equilibrium constant for the combination of the acid dissociation, by which I mean, let's just write that it's acetic acid plus water giving you acetate and hydronium. The base that we have added is ammonia, and that's going to give you ammonium and OH negative. And of course we have the neutralization that's occurring. So reverse of dissociation of water, which is hydronium plus hydroxide, which is giving you the two water molecules. So hopefully you can see hydroxide and hydroxide cancel, hydronium, hydronium cancel, water and water cancel with the two H2O, and you're left with CH3COOH plus ammonia, giving you CH3COO minus plus ammonium, which is the equation I was seeking. Of course, there's a Ka that goes with this, there's a Kb that goes with this, and this is K 1 over Kw. So if I wanted to determine the neutralization or the equilibrium constant for this new reaction, it's a combination of three equations. So I'm just going to say it's Ka times Kb times 1 over Kw. And since I know the values, I'm going to just plug those in. So 1.8 times 10 to the negative fifth times 1.8 times 10 to the negative fifth times 1 over 1 times 10 to the negative 14. And that gives you 1.8 times 1.8. Sounds like I would have close to about 3.24 times 10 to the negative, not negative, positive, because this 10 to the negative 14 becomes a numerator. So I'm going to punch that number one more time. Okay, yeah, positive 4. And that's a smaller number as compared to what we have seen in the past. This too will go a little bit in the forward direction, but realize that it's much smaller as compared to the situation where we had the strong acid, strong base, where we had 10 to the power of 14, or when we had the strong acid, weak base, when our number was to the power of 10 to the power of 9, and then we also did the strong base weak acid combination where it was 10 to the power of 10. So all those were directed all the way to the product side. In this case, it's going to be stuck somewhat in case of an equilibrium. And so for that reason, when we discuss titrations, I'll give you the concept of back titration a little bit, which basically means that you would never be able to carry out a successive direct titration between ammonia and CH3COOH acetic acid, because both of those are weak. But the extent of the reaction really depends on, so in other words, if you wanted to determine the pH of the salt that gets formed, in this case it's ammonium acetate, it depends on the Ka number and the Kb value. Whichever is higher, that is what dictates the pH of the overall solution.